All right. Well, thanks so much for inviting me. This is great. I've known Cyril and Maren for quite a long time, since my graduate student days at Carnegie Mellon. And in fact, my advisor, or one of my advisors, Sebastian Trun, started his work in Bonn as a grad student and with a museum in Bonn. And then later, all the things that we did with Monte Carlo localization was actually an evolution of the work that Sebastian started with Dieter and Wolfram and others in Bonn, and so I owe a lot of that to Bonn for introducing me to real problems in robotics. So yeah, so I will talk about factor graphs for perception and action. And it's a fairly technical talk, but I will try to insert context where needed. So, all right, let's dive in. So indeed, I was actually the chief scientist of Skydio, which is a drone company, and so this is actually the first product of Skydio that I helped build, and mostly what I helped build was the mapping and navigation stack, but also some of the other things that there is a lot of things in this drone, right? And to me, it's still, this is the most advanced autonomous drone on the planet. It's and its secret is actually not so visible. So this is a drone that is built to follow people and film you while you're doing cool activities. Maybe running in the Black Forest or skiing down a mountain slope, or and the drone can follow you and it will not bump into any obstacles. And the reason for that is because it actually has 12 cameras around the perimeter of the drone that give it a full 360 field of view. In fact, there is a second version of the drone, which is the Skydio 2, which was created after I left the company, but was already sort of in prototype stage. And it actually only has 6 cameras, but the cameras are way better now. So you can see that there is actually 3 at the top that are full hemispherical 360 cameras. So they give you a full view of the 360 environment on top of the drone with full stereo. So stereo or trinocular stereo is a technique that you fuse the information from 3 cameras, 2 cameras for stereo, 3 for trinocular stereo, to get a 3D model of the world. And this is not all. There is actually a similar triad of cameras at the bottom of the camera, the bottom of the drone. So now you get a full 360 3D picture of the world. And I'll show a video now on how you can use this in a product. So this is a product video. All the video that you see here is actually shot by the drone itself. So here there's actually 2 drones, one following the other drone to shoot the video, right? And so it has smarts of not flying into obstacles. It knows how to track the person. It knows about camera moves and cinematic moves. So you have an interface on the phone that you can say, give me a droney, or give me a spiral pattern, or just have the drone go out very far and then come back. All these things that it can do with some directorial guidance from the consumer, but it can do autonomously. So you never have to pilot the drone yourself. I mean, you can if you really want to, but Skydio advises against it, because you're more likely to crash the drone than to actually do something reasonable, right? Unless you're a very experienced pilot. So what's the secret here? Well, I'll hope to convince you that the secret partly is factor graphs, okay? The reason that I was hired by Skydio is because I worked on a library called GT-SAM with my students, which is based around factor graphs. And so this is a very early video where you see multiple images, and we extract features from the images. We track those features over time, And from that, we build a map, a sparse map, and also the trajectory of the robot in that sparse map. Okay. So let's see whether yeah, here's the map. It's very sparse. It's just 100 or so points, and then you see the trajectory of the robot or the drone here, right? As a set of coordinate frames. RGB is XYZ, and now you have rock solid geometry, meaning you know exactly where the drone was in that environment. And now you can take the stereo images and do dense 3D reconstruction and blast those 3D points into a 3D model of the world. Okay. And this, you could say, every autonomous vehicle has to solve. So it has to solve these problems of perception, but then also action. So just like estimation looks towards the past, and then action looks towards the future. We also use factor graphs to figure out where the drone will be in the next couple of seconds. Okay. And so the rest of the talk, I will convince you that factor graphs are the right way to think about these things. I will talk about some successes that we had with our group in perception, and success of factor graphs in general in robotics, because it's gone way beyond my group. But then the rest of the talk, I will talk about this new direction that I'm going in with my students, which is using factor graphs for generating action. All right. So why factor graphs? Well, this is sort of one of my favorite slides now to show, because it shows factor graphs in 6 different applications. It gives you a bit of an overview of how factor graphs, what they look like, and how they can be useful to deal with your problem. So a factor graph is really 2 things. You have nodes for the unknown variables. In this case, the first is a tracking application. And so we have x1, x2, and x3 are maybe the location of a person that you're tracking over time. Okay, this could be from the drone, and you're getting measurements of that person in the front facing camera. Deep learning is figuring out which person you should be paying attention to, because it has a model of what the person looks like. And then you're trying to track that person in 3D. Okay, so the second type of node in a factor graph are these factors. First of all, there are factors that indicate a relationship between x1 and x2, saying, well, the person is moving, but the person can't move too fast. We know that you know, if at time 1 the person is at location XYZ, using reasonable limits of acceleration on what a person can do, the person will be within only, like, you know, a meter the next time step, right? And of course, that depends on the sampling frequency of your camera, and on the fact whether you're tracking superheroes or normal people, but these are all just parameters, right? And then the other factors are these measurements. Okay, so your deep learning algorithm has extracted the person and knows exactly where the person is in your camera view, but now you have to tell what that means for the 3D location of the person. So there's factors about instantaneous measurements and factors about motion models. Okay, so I'm not going to say how to solve this just yet, but this is just a representation of how to represent your problem in a factor graph. So in the next application, you could maybe try to add some sophistication. You could add a sequence of binary or discrete variables that model maybe the intent of the person that you're tracking. Or if you're tracking a fighter aircraft, the intent of the pilot. Right, where you can model, is a person taking a large turn to the left or turn to the right, or is she just, you know, running forward? And then you can keep track of that intent over time as well. So now this discrete variable influences the motion model of the person, right? Or the fighter aircraft, right? Or the other drone. So that's called a switching system. And then you can actually also use factor graphs to phrase optimal control problems. Here, x1 and x2 and x3 are a trajectory no longer in the past, but in the future. So where do we want to be 1 second into the future, 2 seconds into the future, 3 seconds into the future? Well, that is influenced by actively changing the motion model using a control inputs, in this case u1 and u2. So we could try to optimize and find out the optimal set of trajectory points in the future and the optimal set of controls to get us there. So optimal control fits in this framework. And then there's other things that I'll talk about in detail about SLAM in the next couple of slides, right? So this figure, by the way, is a figure from my from a journal paper that I published last year on factor graphs for robotics, and that's in annual reviews. And so if you care to know more, that's a good starting point, which gives a very broad overview. So let's talk about a little SLAM problem, and this is actually a slide by Michael. SLAM is the problem of taking a robot and trying to track where it is in space while simultaneously building a map of the environment. So, and I'm explaining this, you know, in a bit broader context because I know the audience is more general than my normal hardcore SLAM audience. So, so a robot, you know, is at a certain unknown location, and then maybe we make a measurement to a landmark. This could be this chair here, right? And then the robot takes a step into the world, and now we know, you know, using a control or an odometry measurement, we know that the robot can't be very far. So this is another constraint. Maybe I'll take another measurement on the same chair, and then maybe it sees a new thing called, you know, which is a table in this case. It might not know it's a table. Maybe it's very agnostic about the landmarks it measures. Maybe it uses deep networks to recognize that it's a table, right? And then it can place that table in the world. And then so gradually you build up this factor graph that allow you to phrase this problem of where am I and where are all the things in the world as an estimation problem or an optimization problem. What is the best set of robot positions and landmark positions that agree with my measurements, which are encoded in these factors, and my odometry measurements, which are encoded in the Markov chain that connects all these robots together. And it's only a single robot. This is a robot over time, right? So in a minute, I'll explain to you how to compute with factor graphs. But one point that I want to get across to everybody in the audience is that even though I'm going to tell you about how they're amazing about, you know, being fast and, you know, they exploit sparse linear algebra, there is something that I've discovered over the last 10 to 15 years about factor graphs that transcends just computational efficiency, which is that, and this was most prominent at Skydio. At Skydio, we drew factor graphs on the whiteboard all the time. So what factor graphs are not only a computational tool to do state estimation or optimal control, but also a mind hack. Now you are talking about your estimation problem in a graphical way to your colleagues on the whiteboard, and you innovate while you're drawing and while you're thinking about this. And once you sort of internalize this graphical language as a way to talk about your specific problem, it becomes a tool for communication and innovation. And I truly believe that. This is not just me sort of doing factor graph propaganda. This is something I've experienced at several companies, right? All right, so let me talk about how we've used factor graphs for doing perception and SLAM, and that led to a number of papers and a number of students that graduated and it was quite successful. But I'll keep it brief and then talk about factor graphs for control, which you might not have thought about, very much. So SLAM, I talked about at a high level, but here is an actual SLAM example. It's very old. I think I made this animation for RSS 2005 or something, which was at MIT, which was the first RSS organized by Sebastian back then. And so the animation shows a robot, and in fact, it's real data. It's part of an old data set that was taken in Sydney. It's actually a truck that's driving in a park, and it has a LiDAR, a laser range-based scanning system, and it detects trees in the scans, and then the measurements are the range and bearings to all the trees in the park. So keep that in mind when you see the factor graph that shows what problem the robot is trying to solve with SLAM, right? So this shows the entire problem in one glance. So you see the location of the robot over time. And this is a truck driving, so we have pretty good odometry. And then these dark blue unknown variables are the unknown locations of all the trees, right? Now I've shown you the factor graph using the solution. So after we solved the SLAM problem, we know where the truck was, we know where the trees were. So I've used that information to graphically represent this on the slide, but of course, in advance, we don't know where these things are. And that's exactly what we're trying to solve, okay? The factor graph, and I won't go into detail, but the factor graph is also the graph of a sparse matrix that is the multivariate derivative or Jacobian of the system. And so the way we actually solve this internally is we take that large Jacobian, decompose it using something called a QR factorization, and do this many times because it's a nonlinear problem, okay? And this exploits all what we know about sparse linear algebra to do this really fast. And the sparsity is in fact exactly given by the factor graph. And these heuristics, I won't go into detail, but they're about how do we, what variable do we look at first? Could we break up this graph into multiple pieces to do this on multiple cores simultaneously? Can we sparsify the graph in advance to make the problem simpler if it's really too hard? Can we use maybe conjugate gradient descent if it's really a dense graph, et cetera, okay? So let me talk about a couple of these things, but on a higher level. So Alex Cunningham graduated around 2013, 2014, who's now at Toyota doing autonomous driving. He looked at the problem of quadrotors, actually. This is years before Skydio, when we're flying multiple quadrotors. So you can build one big factor graph and send it to some supercomputer somewhere and ask the supercomputer to solve the factor graph. You don't even need a supercomputer. It can be just a PC. But sending all the information to a central point is problematic. Because what if the communication doesn't work? What if that computer fails, etc. So what Alex did is, well, let's just break up the graph and try to solve as much as we can locally on each quadrotor, and then communicate only the information between them, right? So this is a distributed mapping paradigm based on factor graphs. Michael graduated around that same time. So Michael Case is now a professor at Carnegie Mellon. He, looked with me to demystify this sparse linear algebra problem of QR factorization, which is all about sparse matrices. But when you look at the sparse matrix, like this, it doesn't mean much. I mean, it doesn't mean anything to me, and it would be surprising if it mean anything to you. So, but he and I showed that you can actually interpret this entire sparse factorized matrix as a tree-based data structure, which we call the base tree. And in fact, we can do incremental inference in using this data structure. So a movie from back then, this is 2012, shows how we use a new algorithm that we call ISAM, and this is the second version, ISAM2, to map, do SLAM over time, and building this data structure, and only changing a tiny bit of the data structure at a time. So as the robot progresses, we build this large tree, which is really the computation that we need to do every time. But instead of solving this with a very large computation every time, because we know it's a tree, we can now only edit the top of the tree. And you can see that only red nodes here are actually changed. And the only time that we have to actually do more computation is when the robot figures out that it took a loop, it did a loop closure, and then we have to do some more computation. Okay, but this is literally this. You can see that it becomes too big to actually see with any amount of detail. But it's literally what is being computed in that algorithm, and it's here. Time is at the top. The current time is at the top, and the past is towards the bottom. So now we have an intuitive explanation of what the robot is actually computing, rather than looking at it as just a sparse matrix that we can't understand. All right, so another success, actually, there is a student from University of Zurich in Davides Karamuzza's group that joined my lab for a while, and I had an amazingly smart postdoc at that moment, which his name is Luca Carlone, and they got together and used factographs and ISAM, the algorithm that I just talked about, to solve this problem of dealing with the very high frame rates information that you get from this device, which is an inertial measurement unit. An inertial measurement unit was made famous in a bad way, or infamous, I should say, because devices like this allow nuclear missiles to reach the other half of the world and hit a target within 50 meters. That is all because of inertial measurement devices. So you have a gyroscope that measures a change in your orientation, and an accelerometer which measures the force on the vehicle, in effect, or the acceleration that results from that force. And you can then integrate that over time. And if you have a very good IMU, you can hit a target at the other end of the world within 50 meters. Now, those very good IMUs are very, very expensive, okay? And they're not in your phone, okay? And the reason is also size. I mean, so the IMUs that are in say a submarine, which is another military application, the IMU of a submarine is the size of a room. And the reason is because the submarine has to be underwater for long amounts of time, and so this IMU has to be amazingly accurate. But an IMU in your phone is tiny and loses track of the absolute orientation very, very quickly, and the absolute position. In fact, if you just implement the algorithms that are used in a submarine on a phone, in 1 minute, these algorithms will tell you that you're past Mars or Jupiter. Okay, so you need to do sophisticated processing and fuse that information with other information that you get from your cameras, from a laser, etc. So Christian and Luca did that, and so they created this super factor, which is called the pre-integrated IMU factor, that allow you to integrate this IMU information at frame rate, at the rate of the IMU, but then only use it in binary factors at the frame rate of your camera. That paper got a Best Paper Awards in TRO, and I can tell you, this is being used in many companies internally, and they won't tell you about it because it's a little bit of a secret weapon. But this has been amazingly successful work. And Davide actually created a new version of the library, the SVO library, that uses this, and released that maybe 2 weeks ago, I think, right? Luca went on to be very successful. He's a professor at MIT now. Christian Forster created a company that was then bought by Facebook, so he didn't do badly either. I had nothing to do with that, even though it happened when I was at Facebook. And then some new things that we're doing now. So this is a slide from a new student of mine, Yetang Zhang. He also did this work actually at Facebook Reality Labs. So this is a collaboration with Facebook Reality Labs, where now we're doing base tree for multiple robots. So we do multi-robot SLAM, and he built something called the multi-robot base tree, or the MRBT, and that was a paper at IROS. So if you're interested in that, I urge you to check that out. All right, so one last thing I would like to talk about, perception, and then I'm going to switch to action. But I want to talk about something that I love, which is continuous representation of trajectory. So, and I'll talk about Chebyshev polynomials. Now, Chebyshev polynomials, that sounds like a complicated thing. It's like, oh, Chebyshev, that's like a Russian name. That must be, polynomial is complicated. So I'm just going to check out mentally until this slide is over. But I urge you, I'm going to give you this amazing story about Chebyshev polynomials, which most of you will now immediately understand Chebyshev polynomials. And it's very relevant when you're working with robots. Okay, so everybody probably knows about the Fourier series, which is, if you want to approximate a function on a circle, okay, then meaning a periodic function, right? So you can see, it's probably hard to see in the slides, but I hope you can see the green circle here. That's actually a cosine wave on the circle, and this curvy thing and in the second column is a cosine of double the frequency, 3 times the frequency, 4 times the frequency, 5, etc. And it's quite well known. I think in Germany you learn this in high school, that a Fourier series, you can just add sines and cosines and then approximate any function that is periodic, to arbitrary precision, by just taking more and more cosines and sines, and that's called the Fourier series sort of convergence theorem. But in robotics, we don't often talk about periodic things. We actually go from one place to another. We start at time 0 and we end at time t. Okay, so a Fourier series which pretends that you're a periodic signal is not the right thing to do. So what you could do is take these cosine waves and just project them onto the midline, onto, in fact, the XZ plane of this little 3D display. And something amazing happens, okay? It turns out that a cosine on the circle, when you project it, when you look at it from the side, you see a line. So in fact, it looks like an ellipse in 3D, and look at it, an ellipse from the side, and you see a line. So okay, you could think that is cool, but it turns out if you take a cosine of twice the frequency and look at it from the side, you see a quadratic, okay? And then 3 times you see a cubic, and 4 times you see a a fourth-order polynomial, etc. And those things are called the Chebyshev polynomials. And that means that the Chebyshev polynomials are basically the equivalent of a Fourier series for periodic functions, but on a line segment. And so all conversion theorems sort of take, go completely from the circle to the line. And so this is, in a sense, the ideal polynomial basis to approximate finite trajectories. Okay. And you can look at I'll skip this slide, but one of my students, Varun Agarwal at ICRA 21, published a paper using Chebyshev polynomials to model both sort of the camera dynamics of a drone with a camera and also the dynamics of the motors. And now we can recover everything about the drone, its motion, the speeds of the individual motors, etc., all in a Chebyshev basis. And so we're borrowing techniques from something called pseudo spectral optimal control, where people have discovered Chebyshev polynomials like years ago. All right, so we're really just copying stuff from another field and applying it in state estimation, which is a perfectly fine thing to do, by the way. Okay, look. So all of this, by the way, you can get for free from the web, because this is all open source software. It's written in C++, but we have wrappers, so you can experiment in Python and in MATLAB. I think MATLAB is maybe less important these days. It's expensive, and all grad students want to work in Python anyway, right? So because of deep learning. But our Python wrapper is really great. It's BSD licensed, so if you have a little startup, you can use GTSAM as a secret weapon. If you have a big company, you can also use GTSAM as a secret weapon. It has a bunch of other things in there, like automatic differentiation, which many people are now exposed to because of deep learning. Well, we've been doing that for 10 years at least. In fact, factor graphs and deep learning libraries are almost the same in this, but in a sense they are different points in the design space of the size of the nodes that you're thinking about, and the number of variables that you're thinking about, and the sparsity of the graph. Which GTSAM is focused on very large, sparse graphs with tiny nodes, and deep learning graphs are tiny graphs with a fairly obvious connectivity, fairly dense. And so there are sort of two design points in the same space. Speaking of secret weapons, there was this amazing DARPA-sponsored competition on putting robots in caves, and it's called the DARPA Subterranean Challenge. And the simulation entry was done by one guy from Barcelona, an ex-employee of All Robotics, who sort of started his own effort. And he worked for months, and he used GTSAM and ISAM in at least 2 different ways to win the simulation component of this challenge. And in doing so, also won $750,000. So he's not giving me a percentage, which is sad, but he did so much work, and I'm so happy that this worked out for him. And he's creating his own company now, which we should watch that space, because that guy is really really cool. So he's doing a company in Barcelona on quadrupeds. All right, I'm shifting in my chair because I'm going to shift gears, right? And I realized that I only have well, I've sort of 20 minutes left if I want to leave some time for questions. So I'm not going to go into super detail, but we're going to shift gears a little bit. All right, so I hoped I convince you that factor graphs are cool for perception. And take my word for it that they are a mind hack in that space. I urge you to check out these articles and GTSAM and start drawing factor graphs on the board if you're not already. Okay. Now I will sort of switch gears a little bit and talk about how we can use factor graphs to think about how to act in the future. All right. And I'll start with some papers that my students and I have written in collaboration with Byron Boots on motion planning. And these are also have won a best paper award at TRO. So I'm not going to dwell too much on them, but I'll explain the setup. So motion planning is acting. So we would, in the case of the Skydio drone, the question is, okay, now we know what the world looks like and we know where the person is. What should we do in the next 10 seconds, right? Where should the drone go to optimally track the person, at the same time avoid obstacles, and at the same time make a beautiful movie? So they are competing objectives, right, that we would like to satisfy. For robots with articulated limbs or humanoids, the question is, how should I move all my joints in the next 10 seconds to not fall over, to go down the stairs, to open that fridge, right? And for autonomous vehicles, it's about how should I change my acceleration and my steering wheel and brakes and to not collide with pedestrians, to follow the route that is being planned by my GPS device, to avoid other vehicles and to respect the rules of the road, right? All of these are motion planning problems. And so we've found out that factor graphs turn out to be excellent for motion planning as well, okay? All these competing objectives can be encoded in factors connected to variables, unknown variables that now encode your trajectory into the future, okay? So we can have motion model factors that say something about the smoothness of your trajectory. You don't want to have a trajectory of a car that is very jerky, right? You don't want to bump into things, so you add factors to avoid obstacles. When you're a robot, you have joint limits, so you cannot use any joint angle. So you need to respect those joint limits. So they can be encoded as a factor. And then we took all the things that we learned from SLAM and said we can apply this in motion planning as well, incremental planning in particular. So this is exactly what Jing Dong, Mustafa Makadam, and Byron Boots did. And I was at Facebook at the time, so I was involved in this work, but they did all this when back at Georgia Tech when I was at Facebook. So really they should take most of the credit for this. So they encoded all this, and so you do planning as inference, which is also, by the way, a German idea. So there's Mark Toussaint is one of my favorite people in sort of planning and inference, and he has a paper called Planning as Inference. So we're really using his idea and applying factor graphs to that idea, right? In a way, all my smarts come from Germany, right? You see this, right? So we have Sebastian and my collaborations in the past with Cyril and Maran, and then now the ideas from Mark Toussaint that we're applying. So I owe Germany a big debt. So this technique that we developed is GPMP2. It uses factor graphs and then also sparsity to do motion planning in sort of an optimal way using all this sparsity algebra stuff, and more using Michael's idea. Michael, by the way, is also German. Michael Case comes from the sort of Riesling area in southern Germany. So he did this base tree, right? And so we can use the base tree for incremental planning as well. And the results that we have with GPMP2 is a method that beats competing methods like CHOMP, which is an older method from CMU, but TRAJOPT, which is a much more recent method. So we do motion planning with real robots with full obstacle avoidance and joint limits, etc., 10 times faster than TRAJOPT does. This is for the 1 and for the PR2. The similar results hold. But things get even better when you're talking about incremental replanning. So if you change your goals, in real time, we can very quickly incrementally replan. And now we're 10 times faster even than our own method, which is GPMP2, and that's incremental GPMP2, right? So we're using these ideas from perception and applying them in motion planning. So that's a theme, right? I've also become quite interested in art and using robots and action for art, right? So here is a paper that we wrote in 2020 on, we give this fetch robot any Unicode. So we're not giving them these images, we're giving them a Unicode. And Unicode is then we fetch the Chinese character from a database, and then we ask the robot for an open loop trajectory planning solution that reproduces the Chinese character in real life. And our results are not amazing. Okay, one of my Taiwanese friends told me that this is very nice. Your robot paints like an 8-year-old in Taiwan. So it's not master calligraphy yet. But what is cool is that every one of these things that we optimize for, these strokes, is parameterized using a little Chebyshev polynomial. So Chebyshev comes in again here, right? We also can encode not just kinematics, but dynamics. So a student of mine, Mandy Shi, published this on arXiv. We can put all the dynamics in a factor graph of the robot and then do kinodynamic planning. So here is a little KUKA robot, which is a German robot, although I'm very sad to report that it was bought by a Chinese company. So it's really now a Chinese robot. And if you look at this animation, this is a motion planning riddle. The robot, this block is too heavy to lift in an obvious way. It will break the robot if you do that. So you have to first bring the mass closer to the body and then go upwards to not exceed your joint limits and torque limits. So this is a kinodynamic planning riddle that that we now solve using factor graphs, right? And so one of the most sophisticated things that we've done is doing robot jumping. So this is a collaboration with mechanical engineering in Georgia Tech, where Ye Tong, the one from the multi-robot base tree, published with his friend Lucas a paper at IROS, where we now build a factor graph that models the successive phases of contact and no contact in a jumping robot, which we then solve using GTSAM, really. We just build a factor graph and then we call GTSAM and ask GTSAM, give us an optimal solution for all the muscle actuation, timings, etc., to jump to a particular height. Okay, so that's just a demonstration that we can actually incorporate fairly sophisticated nonlinear dynamics and actuation schemes inside the factor graph framework and still do this multi-phase collocated optimal control stuff, right? And so let's switch gear to optimal control. And I have probably 10 minutes left. So, but I'm hoping to blow your mind now, and especially, I don't know how many people here. So here's another area where Germany is at the top of the world, is classical discrete planning. Okay, this is the group from Nebel and Freiburg, is really still sort of world leaders in anything that has to do with discrete planning. And of course, many of the students in the audience will probably be very interested in reinforcement learning and Markov decision processes, right? So so here's a graph that shows how you can represent a Markov decision process or a discrete planning problem just as a factor graph. So I'm just going to dwell on this slide for a little bit and then show how you can solve these things. But I'll make a caveat, right? So here's a factor graph of a planning problem. Okay, so we have a discrete state over time, the start state, and a desired end state, and all the states in between. And we have a discrete sequence, a sequence of discrete actions that you can take. And this completely models the strips planning problem. Okay, so you have, if I have an action, then this factor says that the previous state better satisfy these preconditions, and the next state better be a modification of state 0 to state 1 that is compatible with this action. So the effects of the action should be, you know, present in the state at the next time step. So now this factor is maybe complicated, but it really is just a check. If you know planning, there is something, a language called PDDL, which is a sort of propositional language to describe planning. Well, this is just a PDDL formula, right? You add a factor making a constraint on your initial state, a factor where you want to be in, as a goal state. You can add a cost to each action, which is how expensive is it to do that action, and you can add a reward or a cost to the state, which brings Markov decision processes in the same framework, right? So reward or reinforcement learning is all about reward. So you can actually do planning to try and maximize the reward over this finite horizon planning problem. So just take a look at this graph, because I think this is significant. This is the planning problem laid out, okay, with all the planning laid out as factors. Okay, so this is the mind hack. Now that we know how to think about planning as a factor graph, we can maybe innovate in that space, right? Or understand other algorithms old algorithms in a different way. So so one thing you could do is just eliminate the factor graph, and then you get basically an optimal policy at every location. So when you eliminate this, you get actually a base tree, and in the base tree there's arrows that correspond to your optimal policy. So that's one thing. And you can do this from left to right or from right to left, and actually combine both strategies, and then you get search strategies like bidirectional Dijkstra in discrete planning. So we've not done a lot yet with discrete and MDPs, but we've done some things like this with continuous problems. So in continuous domain, your states that you're optimizing over are continuous. Your rewards are quadratic functions of your state. Your dynamics is just a linear dynamics equation of a linear dynamical system. Your controls are now continuous controls, and your control costs are quadratics on your controls. So it fits completely within this scheme. So now this is the entire literature of control, or at least the basis of linear control as a factor graph, right? So, and people know how to solve this in control. This is a finite horizon linear quadratic regulator problem. How to solve it with GTSAM? Well, you just hit optimize, and it will eliminate the factor graph and will give you time varying optimal control policy for an LQR controller. Okay. And once you know that, okay, that GTSAM can just give you an LQR controller, you can think about, well, what if we add sort of crazy constraints in this graph and say, you know, maybe there's state-dependent control limits or foot contact constraints or periodicity constraints or some final state that we really want something, you know, some hard constraint on. So with Carnegie Mellon, with a student from Habichousets group. We published this at ICRA 21. This is basically constraints, equality constraints LQR. So now we just add constraints in the vector graph, call GTSEM, and now we get policies that might depend on more than one state. So again, this is an example of a mind hack. By phrasing LQR as a factor graph problem and optimization in a factor graph, now you're able to very effortlessly extend it to more complicated scenarios that really are a piece of cake to GTSEM for GTSEM to handle. Because these graphs are actually not complicated when you compare them to the complicated graphs that we see in SLAM, right? All right, so you can actually do this with nonlinear dynamics as well. And then you could do something called incremental LQR, which was introduced by Todorov a while ago. And I won't go into the details, but what you can get now is a time varying controller on top of a reference trajectory, which is sort of an optimal controller around the nonlinear reference trajectory. And again, we use that in an art framework. So we had this idea to build a cable robot, which is actually fairly nonlinear, has non-trivial constraints on the controls and kinematics, and use that cable robot to do graffiti art. So my student Jerry actually built this robot. So here is a cable robot and some experiments that we did. It's actually can go very, very fast to speeds of 2 meters per second and accelerations of 20 meters per second square, which we found out through motion capture of graffiti artists is what you need to achieve to do graffiti, sort of in a believable way. And he has done this. So he has, I'm going to fast forward, but what we did is we motion captured the graffiti artist and have him write all the letters in the alphabet. And then we can ask our cable robot to do the same. And it is made possible by basically doing open loop control plans with GTSEM and then developing an incremental LQR controller, which keeps the robot sort of on track around that solution. So now we used optimal control, trajectory optimization, and optimal control around it to do fairly sophisticated things, all in the same factor graph-based framework. Okay, I'll just show you the last couple of seconds of this movie because it's a nice graduate student moment, right, where they're like, yeah, this worked, and so this is one of these successful experiments. Okay, doc. Actually, I'm going to skip the last thing, which is model predictive control, but we developed these methods called STEEP, also by the same students, Mustafa and Jing. This is also in autonomous robots. This is from 2018. And so that combines trajectory optimization and motion planning in the same graph. And that's also something worth looking into if you're interested in sort of model predictive control solutions. And most recently, we've used this in sort of satellite proximity operations, which we do in simulation at Georgia Tech, in sort of a space simulator that Panos Theotras, who's in aerospace, and I'm an adjunct faculty member in aerospace, built in Georgia Tech. And so we're working with companies that operate in space to develop solutions for them. So I'm going to stop there because I'm running out of time. But I hope to convince you that factor graphs are cool. They are a mind hack that you really should be looking into. They have been used in my group very successfully for perception, but we're also branching out in motion planning, optimal control, and model predictive control. And there's a lot of people that have worked with me on this. These are the ones that I mentioned in this talk, but there is a whole host of other people in the perception work that I've not been able to mention. And the bottom are the Skydio founders, which I am indebted to because they really push factor graphs to sort of a new level. And then I'll take questions here on this beautiful graffiti image of GT Sam rendered by our cable robot. So, all righty.